So we'll start. Hello, everybody, and welcome to this webinar that's prepared by the National Center for Geophysics. So following the catastrophic Turkish earthquakes of February 6 and the series of aftershocks that followed, there was an increased request from the Lebanese citizen to know more about the Levant fault or the Dead Sea fault or the Yamuni fault, which are different names for the same fault that's crossing Lebanon from the south to the north, and that has many active branches in Lebanon. The mainly one are the Serghaya and the Rashaya faults to the east, the Yamuni fault in the center or in the middle of the country, and then we have to the west the Rum fault and the Mount Lebanon thrust fault offshore Lebanon. So to know more about this strike-slip fault, we are pleased today to have with us Dr. Yann Klinger. So Dr. Klinger is a research director at the CNRS, the French one, the French CNRS. He is a seismologist, he is a tectonician at the Institut de Physique du Globe de Paris, Université Paris-Cité since 2001. He is the head of the tectonics group in this institute since 10 years. And the work of Dr. Klinger focused on understanding the process controlling continental deformation, and in particular, the major continental strike-slip systems. In this context, he has been working on the Levant fault since 1995, on the part that goes from the Red Sea to Lebanon. He also worked in Turkey on the North Anatolian fault. He mainly focused on long-term deformation, but also on recent deformation through the study of instrumental and historical earthquakes. So in brief, Dr. Klinger is the right person to tell us about the Levant fault, to tell us what happened in Turkey the last 30 days now, and how these earthquakes may affect or not the Levant fault. Before giving the floor to Dr. Klinger, I would like just to pay your attention to the fact that you can write your questions in the chat sections. So you can write them in English, French, and even in Arabic. And I will do my best to ask them to Dr. Klinger at the end of the presentation. Yann, so please.
So thank you, Marlène and the Lebanese CNRS to propose me to present this work. And as Marlène said, I'm going to talk about the Dead Sea fault. And this work is in fact some kind of synthesis of the work I've been doing for more than 20 years now with many collaborators from diverse countries around the entire Dead Sea fault. So quickly, for putting the context, the Dead Sea fault, this is this big transform fault. I hope you see my mouse. Can you confirm, Marlène, that you see my mouse?
Yes, yes.
Okay, so perfect. So this Dead Sea fault is 1,200 kilometers long. It's a left lateral fault that allows the Arabic plate to move northward compared to what is located to the west, what we call the microplate Sinai or the Nubia plate here. So extension in Red Sea, horizontal motion along the Dead Sea fault, and then collision at the north here along the East Anatolian fault where we extrude Anatolia towards the west. So the Dead Sea fault, it's a major structure in the context of plate tectonics. It's quite simple in terms of geometry. As you can see on this plot, it's mostly a straight line with a couple of bends, not too many big branches. And we know well the total offset, so the total amount of deformation since the inception of the fault, which is estimated to 105 kilometers when we take, for example, the Palmyride system connected from here to the western part here, and many other geological features which are offset about the same amount, 105 kilometers. So if we talk about the instrumental seismicity, we have here two maps that shows this seismicity. In fact, this seismicity is quite limited if we look at sensible size earthquakes, let's say magnitude 3 to magnitude 4. You can see here on the left-hand side that the Dead Sea Fault is almost silent. We have a little bit of seismicity at the Lebanese band. Indeed, we have seismicity where the Dead Sea Fault is connecting to the East Anatolian Fault here in the Cyprus subduction. And your eyes are immediately catched by the cloud of seismicity in the south around the 1995 Aqaba earthquakes, also known as the Nueba earthquakes, which we're going to talk about later today. So overall, not so much seismicity, not so much active seismicity along the Dead Sea Fault so far. And then there is a trend to forget that we have this major plate boundary in the Eastern Mediterranean basin here. Also, it's a very active fault. So we have plenty of, I don't know how I can get rid of this. Maybe I can't. We have plenty of evidence for past earthquakes along this, along this fault. Just two examples here. One is this little castle, which is located in Israel, where we have offset walls of an old Crusader castle, which is cross-cut by the fault. In fact, we know this fault has been offset by 2 meters during 2 historical earthquakes in 1202 and 1759. So this is well documented. Also in the Dead Sea Basin, you can see here those sediments. Even if you're not a sedimentologist, you can see that the layers that were deposited flat are not now totally folded due to the shaking related to some earthquakes here. So we have plenty of evidence for past large earthquakes along that fault. Okay. So can we get rid of this? No. So simple geometry and kinematics, which means simple motion. We know the total offset. We know we have large earthquakes. And we also know that we have a large population, about 8 million or more, in a distance less than 100 kilometers from the Dead Sea Fault. So there is a real concern for hazard along the Dead Sea Fault. So the Dead Sea Fault is in fact a good target to better understand strike slip fault in general. And today I want to focus on 2 specific points. I want to tell you more about the rate of deformation at a multiple time scale. So what is the speed of the deformation along the Dead Sea Fault? And I also want to make a little summary of what we know about earthquakes along the Dead Sea Fault, because indeed, this gives us some clue about what could happen in the future. So let's start with the instant deformation. So one way to measure instant deformation is to use GPS. And to do this, we've been working mostly in the southern part of the Dead Sea Fault. You can see here the Dead Sea Basin. You recognize also the Gulf of Aqaba right here, and the Lebanese borders, which is just north of my figure here. And several times we were able to deploy GPSs across the fault here, so building long profiles that allow to measure the displacement, the horizontal displacement from one side compared to the other side. So again, as I said, this fault is left lateral, meaning the Sinai microblock is moving southward compared to the Arabic plate here. So if we look at those results, we have here all our measurements, which were measured 3 times between 2009 and 2004, and 2012. And everything has been placed here in reference to this station Ramo. So Ramo is fixed, is not moving. You can see that most of the stations on the Sinai microplate here are just not moving, saying all this plate is consistently behaving like a block. And when you move eastward, you get away from the fault, from the fixed point, you see that when you cross the fault, you start to have the GPS vector getting larger, which is very consistent with a locked fault, so a fault which is not moving during the entire seismic period. And here, those vectors on the far field east show the long-term motion. So you can make a profile across all those vectors. This is what you have on the right-hand side. And on the top part of the right-hand side figures, you have the fault motion parallel to the fault. which shows this very nice arctangent profile, very classic from a locked fault, locked strike slip fault. And from this, we can measure the modern slip rate, which is 4.9 plus or minus 1.4 millimeter per year. So this is the slip rate today as of a time scale of maybe 20 years, 4.9, so let's say 5 millimeter per year of deformation along that fault. On the lower part here, what you see the deformation perpendicular to the fault, and you see that on average is 0, meaning that we have no real extension or compression across the Dead Sea Fault, at least in this southern part. We have only horizontal motion along that section of the Dead Sea Fault. So more recently, we've been able to measure also the deformation directly along the Gulf of Aqaba. So again, the same structure. So it's interesting to see if the slip rate is changing along strike along the fault. And in fact, you can see that again, here we have 3 surveys between 2015 and 2019, and they led to the same kind of slip rate, let's say 5 millimeter plus or minus 1 here. And you have the 2 profile on the right-hand side that shows all the data points, mostly on the Saudi side where we have our data points, as there are very few measurements, unfortunately, on the Egyptian side. Something which is interesting because it would have consequences in terms of potential earthquakes is that the locking depth, which means the depth at which the fault is locked, where the fault is not moving, seems to be shallower in the southern part of the Gulf, suggesting that we have less potential for large earthquake there. So something which is really interesting along the Dead Sea Fault is that we can do different measurements of the slip rate at different time scale along exactly the same profile, at exactly the same place. So we can compare different time scales at the very exact same location, which is very uncommon for big continental fault. So here I'm going to show you some measurements of slip rate over the Holocene. So the Holocene, for those of you who are not very familiar with geological time, this is a time since the last deglaciation. So let's say it's about the last 15,000 years. So it's geology, but recent geology. And I'm going to take you at one site, which is the blue square right here. And you can see that this site is in fact just located where we had the GPS profile as well. So we will be really able to compare those 2 methods here. Because I'm not sure you're very familiar with the quaternary geology methods, I'm going to take you step by step so you really see what we're doing. So now on the left-hand side, you have a Google Earth view of the Wadi Araba, this big valley between the Dead Sea Basin and the Gulf Aqaba. You can see the road for scale. We're looking eastward toward Jordany. And you have those big rivers that come from the Jordanian plateau and flow in the valley here. And you can notice right away that we have those dark patches, which are gravels. This is a big alluvial fan. And those alluvial fans are cross-cut by linear features. You can see here, which are now outlined by the arrows. And this corresponds to the trace of the fault in the field. On the right-hand side, you have, in fact, a view, a satellite image, where we show exactly the same thing. You recognize the dark patches, which are pieces of the alluvial fan, older, and you have the active riverbeds, which are showing in light color, light gray colors. You see the road for scale. And so what we can see already here is that we have rivers which are entrenched, so like in a gorge between patch of land which are uplifted, prevented from any action from the river, and so preserved. And so why we have such a geometry? We have this geometry because we have a little kink in the fault, a little change in the geometry, which makes here the land going uplift. So we have a little bit of vertical deformation in addition to the strike slip. If you look at the right inside on the lower part of the screen, you will see a shot of the surface, what we call desert pavement. And we see here those surfaces which are abandoned by the river and now that just evolve through the arid conditions. So if we map those surfaces, now we start to see better. We see this old surface in orange. We see the gullies, the river that go across it. And if we look at details here, for example, the left inside plot, we have this gully C3 that goes in between two big patches of this old surface F3. But very interestingly, on the lower part of the river, we also have this dark patch here that looks very much like the F3, but it seems to be not in front of the current river. So we want to use this to talk about the offset, the horizontal motion of the fault. So on the lower part of this plot, you have a field view. You can see the white triangle is showing the viewpoint, in fact, and you have the people for scale here who are standing on the top of F3. So this dark patch is now called F2, and we see it outside the gully, but we also see a little piece inside the C3 gully. So when we say, okay, those two surfaces are the same, maybe we can try to connect to see how much the lower part has been moved relative to the upper part and how much we need to move it back in front of its original position. So this is again more mapping. Now you see the current flow, F1, and on the lower part, you see in the field those different surfaces, F3, the oldest one, F2 already abandoned, and F1, the active flow of the channel. So if we take this piece of satellite imagery, this is spot imagery. The resolution here is about 10 meters. You recognize the fault in the middle, these vertical discontinuities, and on the left part, you see this very dark patch, which is this piece of alluvial fan. Here is a map for better explanation, where you find this piece of the alluvial fan here, and a little remnant of the same surface inside the gorge of C3. So what we do here, we note that the shape of the alluvial fan, in fact, looks like more like the half of the alluvial fan. And this is emphasized by the shape of the rivers here that are radial, and they all point to the apex of the fan. All the northern part of the fan, has been eroded by the active river during big storms. So what we want to do is to take this fan and bring it back to its original position, and then we will be able to measure the offset, the motion of the fault since the emplacement of this fan. So there are many ways to do it, but this is our best fit here, where we put the apex, the top part of the alluvial fan, in front of the center of the feeder here. This corresponds to an offset of 48 meters. So now if we want to know the speed of deformation, what we call the slip rate, we need to know the age of this surface. So this is something else. We need to go in the field. Oh, yes, before we do this, we want to be sure that, in fact, we can find similar evidences along the fault. So we were playing with that guy, but in fact, we can do the same game with the next gully here, and there are other evidence further south. So this measurements of offset is in fact quite robust. It's not only one measurement, it's several measurements repeating along that section of the fault. So now we need to date these things. So to date these things, one way is to collect sample on the surface, so gravels. And in this area, south of the sea, we have plenty of quartz, and quartz, without getting into the details, what we need to know is that the minerals that include oxygen and silicium, and it's taking a lot of cosmic rays, like the ray of the sun to be simple. And when they get this, they change to beryllium-10. So what we can do is try to measure the quantity of beryllium-10 atoms inside our quartz. So just to give you a sense of what it is, it's like we would look at people on the beach, and depending on how much they are tan, how darker they are, we could try to assess how long they've been on the beach. So similar to people on the beach, I mean, you can come to the beach with already some colors. That's what we call inheritance. Indeed, depending on your position on the beach, on the clouds and things like this, you will not take colors at the same rate. This is a production rate. And as you all know, when you are really colored, you start to peel. So you start to lose some of your colors. And this is a decrease, this is erosion. So it's worth saying for people on the beach, it's exactly the same for our rocks on our field samples. So we can collect samples on the surface here. We can also collect samples on the top surface. So you have a little example of such kind of sample on the left down part of the screen. This is a piece of granite, which includes this quartz. And so we can measure how long they have been sitting at the surface of those surfaces. And we see that we have two clusters of edges. The lower part, the F2 surface here, has all its samples consistent, and you see that all the samples have been deposited around 12,000 years. So it means at 12,000 years, this surface was emplaced by the river and then not touched anymore. If we look at the samples that were collected at the top part on the older surface, it's very consistent with the age we can measure, and they are 55,000 years old, so much older than the young surface we're interested. So now we can really derive the slip rate for this surface, because we have distance, 48 meters of offset, and we have the age of the surface, about 12,000 years. So this leads us to a rate of, again, 4.6 millimeter per year, which is about 5 millimeter per year over 12,000 years. So this is really interesting. This is really interesting because we have the same slip rate, the same deformation rate over a very short time scale, 20 years from the GPS, and over several thousands of years, like the Holocene period. Okay, so in some places, the deformation is not that straight, and we have more specifically the Lebanese band. And so you have on the right-hand side here a map of Lebanon, topographic map. You recognize Beirut here, Tripoli here, Saidat. And we have the Yamune Fault, which is this very nice lineament that cross-cut the mountains. Tergaya Reshaya, which are right here across the Bekaa Valley. But we also have here bathymetry, so topography under the sea. And you can see from this map that under the sea is just not flat. We also have geological structures here with canyons. Those canyons are disrupted, and we have those topography, which in fact are folds. So if we try to make interpretations, this is the work of one of our former students at Elias. And you can see that here we can define the trace of the Mount Lebanon thrust, which is compression, so deformation, but creating vertical motion in addition to the horizontal motion related to the Yamune Fault. So in Lebanon, because we have this kink in the direction of the fault, which is roughly north-south and takes like a 10 degrees eastward kink in Lebanon, in addition to the horizontal motion, we also have compression, which is mostly accommodated by this offshore Lebanon thrust, which is going under Lebanon. So can we see traces along the coast? Yes, we can. In fact, if you go along the coast of Lebanon, in many places, you will find uplifted shorelines, exactly the kind you can see on the upper left of the screen here. You can see these platforms which are outside the water. And so those platforms are in fact formed by some kind of animals called vermetid. So those animals, they do what we call bioconstruction. So they kind of build their own cement like some kind of coral, and they need to be underwater to live. So what we see along the coast of Lebanon is that we have those platforms which are now out of water, so they have been uplifted by some kind of deformation, very likely deformation related to earthquakes along the Mount Lebanon thrust. Can we date the last earthquakes along the coast? We can try. In fact, because those are live organisms, they have C14 carbonate material, so we can date this organic material. And we see that all those platforms that we see today above the sea level, the animals, they all died just after 551 AD, which is the date of a major earthquakes in the oriental basin of the Mediterranean Sea. So in fact, this is a way to prove that the Mount Lebanon thrust was very likely the source of these major earthquakes that affected Eastern Mediterranean. So we have evidence here for activity along this fault of Lebanon. So as I said, in Lebanon, we have this partitioning of the deformation between the on-land deformation along the Yamune fault and the offshore thrust. So we can summarize this here with full strike slip along the north-south section here, slower motion along the strike slip section in Lebanon because part of the deformation is accommodated by the Mount Lebanon thrust here. All right, so just to summarize this part, in fact, we can now put all the data which are available along the Dead Sea Fault for slip rates. So this includes the data collected by our group, but also by other different groups. And you can see going from south in the Gulf Aqaba, we have GPS measurements around 5. We have geologic measurements here around 5 again. This is again GPS. This is geologic rate again 4 to 5. Geologic rate. These trenches we can discuss later. And then when we go to the north, we again have geologic rates, which are in fact quite fast, but still close to 5. And we still have this point here, the Al-Shabi et al. Study, which is much slower. This is a GPS point. We can talk about it at the very end of this talk because it's very interesting to suggest that this fault is in fact going slower on the northern section compared to the southern section. But overall, what we can see here is that we have a very good agreement between geologic rate and geodetic rate. So we have a very good agreement at all time scales with a slip rate of 5.1 millimeter per year. And in fact, this is very consistent with what we see from all major strike slip fault over the world. As you can see on the right-hand side here, where we have a comparison between geologic rate and geodetic rate for most of the strike slip fault on the planet, they all align along the 1-to-1 line. So in that sense, the Dead Sea Fault is well behaved as many of the plate boundaries on Earth. Okay, so we spoke about long-term deformation, but how this deformation is accommodated. This is what is interesting us today. So as I said in my introduction, we have very few significant instrumental earthquakes which are known, but we know a lot about past earthquakes. We have a very nice historical record in the Dead Sea area, and we can also talk about paleo earthquakes, so earthquakes that are recorded in the geological setting. So with this, we can try to build a spatio-temporal earthquakes catalog for the Dead Sea Fault. So how to locate old earthquakes? I mean, again, building on the Lebanese case, for example, looking at historical archives, we know that in May 1202, we had a major earthquakes that produce damage and destruction in all the red area here, which reported macroseismic destruction. One famous site is the Jupiter Temple in Baalbek, where many of the columns did collapse in 1202. However, just based on the distribution of damage here, we see that it's very hard to decide which fault is a causative fault because we have a set of different faults which are included in the macroseismic area. Another example, in 1759, we had another earthquake, roughly magnitude 7.4. Again, the Baalbek temple was affected. You can see on the left-hand side a very nice keystone, which has moved during the earthquakes. Also, it didn't fail, so it didn't collapse. And again, you can see that just based on the macroseismic data, it's very hard to decide which fault between the Yamune or the Rashaya-Surgaya system was causing this earthquake. So if we want to really move forward with the hazard assessment, we need to be able to really attribute historical earthquake to very specific fault. So to do this, we need to change tactics, and one way to go is to work with paleoseismology, and I'm going to give you one example here in Lebanon, where with some students, we work on the site of Yamune Basin here in the western side of the Bekaa Valley. So what is the Yamune Basin? We have the fault. The fault is making a little kink here before continuing this way, and this kink here produces some extension. Some extension means we have a basin with a lake in this basin. This lake has been drained in 1930s. But before that, we had a depression with fine sediments collected in the basin. So this is very interesting because we have what we call a very nice stratigraphic sequence, many layers of lacustrine sediments, and each of these layers, in fact, full of organic material that can be used for dating. So here we had the potential to really build a nice catalog for historical earthquakes along the Dead Sea Fault. So just if you're not familiar with paleoseismology, how does it work? If we look at the left-hand side here from top to bottom, pretty much we are at the bottom of a lake. So we pile up layers, they are flat, and then we got an earthquake. So the earthquake will rupture the ground surface, will offset the layers, making cracks. And then later on, we continue to put new layers that will bury the rupture because the lake is still here. And so we can define what we call an event horizon, which is this limit between the units that were affected by the earthquakes below the earthquake's horizon and the units we are post-dating the earthquakes and which are above the event horizon. If we are able to date material in those two units which are bracketing the event horizon, then we can get an estimate of the age for this earthquake. And this can happen several times in our stratigraphic sequence. So typically in the center image here, you will recognize some bed of coarser sand and some finer units. And you see that they are disrupted in several places. And this is due to deformation related to earthquakes, as you can see on the right-hand side picture. So using this kind of process, we can build, for example, in the case of the Yamune Trench, a very nice record of earthquakes. And in that case, we were able to recognize up to 14 earthquakes in the past over about the entire Holocene, so about 12,000 years. So we're not going to talk about these 14 earthquakes today, but just to stay on our example and try to find out which fault was responsible for the 1202 earthquakes, which was the last major earthquakes in the area, we can focus on the top part of the record here, the most recent earthquakes, and building on all the dates we have for the different layers, we can show that at that site, this fault did not move since after 1270 here. So in fact, we have no evidence of rupture past the 13th century. So the last earthquake along that fault has to be 1202. So here we can demonstrate that along the Yamune fault, the most recent earthquakes has to be the 1202 earthquakes. So with this kind of work, now we can start to put our past earthquakes on the map and to attach them to specific faults. So the Yamune fault, who hosted the 1202 earthquakes, the Sergaya-Rashaya fault, the hosted the pair of October and November 1759 earthquakes. We also mentioned the Mount Lebanese thrust that did host the 551 earthquakes, and we have the Rum fault here, which hosted the 1837 fault for the Lebanese fault so far. So we start to build a catalog with location and time of past earthquakes. This is only timing, right? So if we want to talk about magnitude, we also need to be able to talk about displacement. As you've seen for images of Turkey, where you've seen many infrastructure are horizontally offset, this is a way to measure magnitude. So in our trenches in Lebanon, we were not able to do this, but we were able to do it a little bit further south here in another site called the Beteiha site, just north of the Sea of Galilee. So in that place, we are in the middle of the field in a very flat area on the seashore of the lake. And in fact, we can find an old river, an old channel, which is now dry, but that was crossing the fault. And so this channel here is expected to be offset on the left inside. So what we did open trenches everywhere at the outlet of this little channel. Here you can see on the right hand side the map view of all the trenches that were open. On the left hand side, you can see how it looks in the field. It's a little bit messy. We opened many trenches over 3 years. But at the end, what we can do is we can reconstruct the geometry of the different channels that were crossing the fault. And so in that way, we can reconstruct the horizontal motion associated with past earthquake here. So this is very interesting because in addition to timing, we start to be able to also put together offset displacement per earthquakes, which is needed to get to the magnitude. So here you have a 3D view of all the walls of the trenches, just to look for those channels, which are not so easy to recognize in the field in real. So here is just a little example. We have a map view. All the squares are just the outline of the trenches, and we can correlate our channels from one trenches to the other one to just track the channel across the system. And so at the end, when we put in front of each other the two sides of the channel, we can assess the amount of motion for each earthquake. For example, the channel 2 has been offset by 3.3 meters, and we can date the units inside the channel to the 7th to the 9th century. Channel 3 is a bit older, and in fact, it has been offset by 4.4 meters in 2 earthquakes, and we can date this channel to the 5th to the 7th century. So now we have timing and amount of offset for different channels. So at the end, we can build this nice time series. So x-axis is the time, y-axis is just a probability because it's a little bit more complex than just time and offset. The time depends on your quality of your samples. But we recognize our 2 most recent earthquakes, 1759 and 1202, and a bunch of older earthquakes that we can tie to historical earthquakes. Because we have also the horizontal motion associated to each of those earthquakes, we can build this lower plot where you have time for the x-axis and horizontal motion for the y-axis. And each box corresponds to 1 earthquake. And so you can see that if you average everything over 2000 years, the slope of this straight line gives you, again, the slip rate, about 5 millimeters per year, okay, which is what we already knew from GPS and from geology. So earthquakes tell us the same story. However, you can also see that the distribution in time of the earthquakes is just uneven, with some time period like the last millennium where we had only 2 earthquakes, while early in the beginning of the current era, we had a flurry of earthquakes. So depending the time section, because the earthquake's distribution through time is not regular, it looks like we have change in the slip rate at a very short time scale. But average slip rate is always the same. So this is very important to keep in mind. Earthquakes do not necessarily occur always on a regular basis. So we did the same kind of work along the southern part of the Dead Sea. I'm not going into the detail here, but we have several sites where we could at least build the catalog, the time catalog, not always the horizontal motion. So just 2 sites. Again, we have a nice stratigraphy in those places. We have, again, nice records. So this is one example where we were able to here identify the most recent earthquakes. You can see all the cracks that end below this unit. So this green unit at the top post-date the last earthquake. So if we can date it, we can put some constraint on the very recent earthquakes, but you can also define 7 other event horizon. And so at the end, we are able to find evidence here for 8 to 9 earthquakes in that trench. And to date those, thanks to carbon-14 dating. So this is just a view of the time on the x-axis, and on the y, you have the pile of sediments and samples, and in red are indicated the potential dates for those earthquakes. And because we are in the Middle East, where we have this incredible historical record, in fact, we can cite those earthquakes to earthquakes which are reported in the historical document. And among those, at least one is very well known in the entire region. It's a 1068 earthquakes, which is reported to be a massive earthquakes all around the Middle East here. So again, we have those sites where we can see multiple earthquakes. And from there, we can build an earthquakes catalog. So the 2 sites I've shown are here and here along the Dead Sea at the top, Gulf of Aqaba in the south. And now we can try to discuss the lateral extent of the rupture, lateral extent that using scaling laws of geophysics allow to discuss magnitude. So here we have the summary of all our earthquakes along the Dead Sea section, and maybe we could include also the Yamune section here. And if we put all this together, we can see how earthquakes are in fact accommodating the large-scale deformation measured with GPS or geology. So on this little plot here, it's again the same story. We have distance along the fault here, our different paleoseismological sites, Jordan Valley again, this is Taipei, this is Qatar. And all these blue bars are the historical earthquakes that we can see at the different trench sites, and which are usually known from the historical as well. So now we have timing and we have lateral extent, length of the surface rupture for each of those earthquakes, so we can talk about the magnitude. So to do this, what we will do is again using scaling laws that relate length of the rupture and magnitude, and we can try to work out the way we accommodate the long-term deformation. So this long-term deformation, here you have distance along the x-axis, displacement along the y-axis. And so from our geologic rate or GPS rate, we can say, okay, for example, over 2000 years, we have accumulated about 8 meters of displacement if we talk about a little bit less than 5 millimeters per year. Okay, this is what was loaded by the tectonic system. Now, earthquakes, each time an earthquake happened, it accommodates some of this deformation. So depending on the assumption we do on the length of the rupture, for example, along that section, here's the south, if we take big earthquakes, in fact, each of these big earthquakes will have several meters of offset, so over 2000 years. For all the slip accumulated, this is a red curve, we have accommodated all the blue curve thanks to earthquakes. Indeed, we can do different scenario with smaller earthquakes, so more often but smaller. which means we accommodate less deformation for each earthquake. So at the end, the difference between what has been accumulated and what has been accommodated by the earthquakes is larger. And so this is the key. How much is this difference between what has been accumulated and what has been accommodated? If we take the highest assumption, we can see that pretty much everywhere along the Southern Dead Sea Fault, we still have about 2 to 3 meters of slip ready to go. So this is potential for earthquakes of the size 7.3, 7.4. And if we look at the more worrying assumption, meaning we have mostly smaller earthquakes, it means that we have now a potential for 4 to 5 meters of slip anywhere along this section of the fault, which would correspond more to 7.4 to 7.5 or 7.6 even. So this is just a way to look at the potential for earthquakes along this section of the Dead Sea Fault, where we have a lot of information. So to finish with this story, we can look at the most recent development. We have been working most recently along the Gulf of Aqaba, which is the southern end of the fault. It's underwater, so it's a bit more difficult. But we know the fault is here. We also know, you probably know, that there are big developments which have been started on the Saudi side with a big urban center, which is currently being built, the NEOM infrastructure, and there is also a project for a bridge across the strait here of Tehran. So we need to know what's happening in this place, because this is the only place where we have evidence for large earthquakes, the Aqaba earthquakes, magnitude 7.3 in 1995. In the field, we could see surface ruptures, so you can see how the hill has been disrupted vertically by the earthquake. We could work on the aftershocks, so many aftershocks, which are smaller earthquakes after the main shock. And so the question is, which fault is a causative fault? Can we have larger earthquakes in the Gulf of Aqaba? So this is what we knew from the 80s. This is a very crude bathymetry from the Gulf. And so very recently, we had the chance to run a new cruise in the Gulf of Aqaba, so we can come up with a new bathymetry of the entire Gulf. And you start to see really very nicely the detail of the fault here, and we can propose a new model for the fault zone in the Gulf of Aqaba. And we see we have very clear, distinct sections. And so the question is how much those sections can break separately or can break together to make major earthquakes. So in addition to do bathymetry here, we also try to collect information about past earthquakes activity in the Gulf. And so, yes, before talking about past earthquakes, I just want to show you some evidence of the most recent earthquake, the 1995 rupture. You can see here on this detailed bathymetry, the trace still very sharp of the fault right here that was breaking during the 1995 earthquake. So with this kind of data, we are really able to see details of the actual co-seismic ruptures. So the ground ruptures at the bottom of the Gulf. Okay, so if we look at this here and we say the rupture was about 40 kilometers, we had a magnitude 7.3 using scaling laws. Again, we know that the horizontal displacement had to be about 2 to 4 meters. So the question now is, do we have potential for even longer rupture along the southern section of the Gulf? So to do this, we also collected some cores in the Gulf here to look for turbidites. So turbidites are those big mass wasting motion triggered by earthquakes underwater. And we found evidence for past earthquakes. Okay, so there is still many questions for the Dead Sea Fault, how it connects to the Red Sea. How do we explain the discrepancy between the slip rate at the north? I said that in Syria, the slip rate seems to be slower than in Lebanon or even further south. Does it impact earthquake cycle? Can we have very large earthquakes, and how large? Can we have a large tsunami for the Gulf of Aqaba? So I guess this is less an issue for Lebanon, but still it's important. And so before I stop, I just would like to bring 3 more slides about what happened about a month ago. So what about the February 2023 earthquake sequence, which are where just North Lebanon is just located south here. And this is where we had the rupture of the 2 big earthquakes. So first to say, those earthquakes, they happened on very well-known faults, the East Anatolian Fault, which is accommodating the motion of the Anatolia block relative to the Arabian block. So they are, again, strike-slip, so it means horizontal motion. And we know that the slip rate along the East Anatolian Fault is about 1 centimeter per year, so twice the rate of the Dead Sea Fault. And so we had those 2 major earthquakes, magnitude 7.8 and 7.6, in fact. So they are very large earthquakes for continental earthquakes with a lot of horizontal motion. Just one example, but I'm sure you've seen many of those, of this road, which has been offset by the earthquake. So indeed, this is a concern, but this is not really a surprise. If we use historical data and paleoseismology for the area, so you recognize this broader map here with Lebanon in the lower part of the map. You recognize 1202, we mentioned about it, that ruptures the entire Yamune Fault. 1759, that ruptures the Hashaya-Sergaya system. And we know we had earthquakes during the 12th century that broke the Syrian section of the Dead Sea Fault, all the way to the connection with this East Anatolian Fault here, where we also have evidence for past earthquakes. Namely, the 1822 was probably a major earthquake along one of the branch that ruptured, and we have again earthquakes in the 12th century. So during February, we broke very long sections of, during 2 earthquakes, we broke very long sections of the East Anatolian Fault, but not affecting so far the southern part of the northern part of the Dead Sea Fault. The northern part of the Dead Sea Fault is not the only fault in the area. We should also keep in mind that this system is in fact splitting between the Dead Sea Fault and the Cyprus subduction, which is going westward here. So the only thing we can do right now, and it's important in the aftermath of the earthquakes, is try to understand a bit better how these most recent earthquakes have redistributed forces. And without getting into the detail, we can use the preliminary result of the deformation accommodated by this earthquake to compute what we call the Coulomb stress changes, so the redistribution of forces following these earthquakes. And you can see that the places which have broken are in blue, meaning the forces have been decreased, while some sections are really in red, which are places where the amount of accumulated forces has increased and where we expect to have more aftershocks and triggered seismicity. And this is true that the northern section of the Dead Sea Fault is in fact in the red quarter. Also, it's not that red when you go south toward Lebanon and further south, but indeed the amount of loading has been increased a little bit and could trigger microseismicity a bit more than usual. And indeed, over the long term, it will increase the chances for major rupture along the Dead Sea Fault itself. This being said, it's not a forecasting, okay? It's only a calculation. It has very significant assumption behind this kind of calculation. We would need to do much more work to incorporate historical earthquakes, to incorporate long-term loading to make this kind of plot much more accurate and useful for discussion. And I think with this, I will just stop and take questions if there are any questions. Thank you very much.
Thank you, Yann, for this very informative presentation that told us a lot about the study that have been done so far in the on the Levant Fault. And then you end up, of course, with this couple of slides, you know, that maybe trigger a little bit of questions.